Bismillahirrahmanirrahim. Now let's come to the second part of this lecture. I just want to make some thing more clear. That was the second moment of area, and that second moment of the area was equals to when I selected that one is that was I was equals to 1/12 BH cube, right? This was I was equal to BH क्यूब, राइट. सो मैंने वहाँ पे एक आपको कॉन्सेप्ट दिया था कि जिस वक्त आपका एक आपने लकड़ी का पट्टा रखा हुआ होता है और जिस वक्त आप उसके ऊपर से गुजरते हैं, ठीक है, तो इट बेंड्स. फॉर एग्जांपल अगर वो इस किस्म की शेप है उसकी, राइट, दिस इज द शेप ऑफ दैट पर्टिकुलर वन, और वो बेसिकली कुछ इस किस्म का है जिसमें आपकी ये जो है दिस इज हाइट और दिस इज योर बी. अब अगर मैं इसको 90 डिग्री पे फ्लिप कर देता हूँ, ठीक है, 90 डिग्री पे अगर मैं इसको लेके जाता हूँ तो अब क्या होगा, अब इट विल बी लाइक दिस शेप, राइट. और इस शेप में बेसिकली आपका कुछ इस किस्म का ये एक्सप्रेशन आ जाएगा, ठीक है. ये अब 90 डिग्री पे चला गया, ठीक है. इन दोनों का बेसिकली जो है डजंट मेक एनी डिफरेंस कि आप आई एक्स ले रहे हैं आई वाई ले रहे हैं, ठीक है. अच्छा, अब क्या है, बेसिकली एच इज लेसर देन द बी, right, in comparison with this one. In this particular case, this is your B and this is your H, right. So I of this will be far greater than I of this shape, since I told you in the last lecture that I relates with the stiffness. So if I is greater than for this shape, so the stiffness will be higher, and when you will apply load into this direction on this, so it will never bend as compared to this one. इसी वजह से जब वो चौड़ा पार्ट ऊपर होता है और ऊपर से गुजरते हो तो it always bends. अब अगर उसी चौड़े पार्ट को मैं खड़ा कर दूंगा इस तरह 90 डिग्री के ऊपर ले जाके, तो अब उसकी हाइट जो है, जो पहले उसकी विड्थ थी, वो अब उसकी हाइट बन गई है, और हाइट का क्यूबिक रिलेशनशिप है, ठीक है. तो आई ऑफ दिस वर्टिकल शेप विल बी फॉर ग्रेटर देन द हाइट आई ऑफ दिस हॉरिजॉन्टल शेप. तो इसी वजह से जिस वक्त आप इस शेप के ऊपर से गुजरते हो, ठीक है, तो इट ऑलवेज बेंड्स बिकॉज इट हैज लेसर मोमेंट ऑफ इनर्शिया एज कंपेयर टू दिस शेप, जिसके जब उसके ऊपर से आप अगर गुजरने की कोशिश करोगे तो इट विल नेवर बेंड. इसी वजह से जो आपके पुराने घरों के अंदर जब लकड़ी की छतें होती थी, ठीक है, तो उसके नीचे जो शतीर लगे वो हुआ करते थे, वो बेसिकली वर्टिकल पोजीशन में, उनकी हाइट ज्यादा होती थी, विड्थ कम होती थी, ठीक है. इसी वजह से कि जिस वक्त उसके ऊपर लोड आएगा तो इन एनी केस दे शुड नॉट बी द bending over there, right. So this was the one concept which I want to make clear before the starting my second part of this lecture. Now I am going to share the presentation now. Right, so we were here, right. So if the pure bending, since we are dealing with the pure bending, so if I start my video so that you can look at me. So if this is the positive bending, because the bending is in the y direction, positive y direction, right. And if I bend this into this one, so bending is into the negative y axis because it is going in this way. So न्यूट्रल एक्सिस के रेफरेंस से it is in the negative one and it is in the positive y direction, right. So this bending, this is the curvature which it is making, right. So this is the positive bending towards the positive y axis, and this is the negative bending towards the negative y axis, right. Now let's start some mathematics. Since we have already discussed that there is no rotation involved, no angular deformation involved, since there is only change in the length, upper is under compression, lower is under tensile, so there is only change in length, right. So there is no shear stress involved. Top surface is contracting, bottom surface is expanding. Since there is a change, so we will deal with only sigmas and epsilons, right? Normal stresses and normal strains. Okay, there is a line that is called neutral surface. Here it is called neutral axis, on which strains are zero, resultingly stresses are zero. This is what we have already discussed in detail in many times, right? So now this rho over here, you can see this is the rho, right? This rho is basically the this rho is basically the radius of the curvature, and this is the neutral axis, right? So we know that epsilon x is less than, because compression is there, so epsilon x will be lesser than 1, lesser than 0, and neutral axis it will be 0, and on this surface it will be greater than 0, because tensile forces are there, so resultingly tensile strain will be there. Here it will be the compressive strain, so compressive strain is always negative, so it will always be less than 0, and on the lower side tensile strain, on the top surface it is a compression, and in the lower surface it is the tensile. So tensile is always positive, compression is always negative. So topmost surface, this inner surface will be in the epsilon x will be negative. On the lower surface epsilon x will be, normal strain will be positive one. In this and y, and in this particular case for compression from the neutral axis, y will be positive 1, greater than 0, and in this particular case y will be less than 0, because your reference axis is existing on the neutral axis. If you look at over here, right, it is in the reference axis over here, and reference axis is existing on the neutral axis, right? So now if we want to calculate epsilon x will be del extension over the original length. And what is the extension? Rho is basically, we know S is equal to R theta, right? So theta will be there because angle is this theta. R, what will be the R? R is, in particular case, original R is rho, this one, and the deformed, after the deformation, this surface is basically the surface which is going to be shrinked. So if this is the y distance, if we are taking this at a particular distance y from the neutral axis, so it will be rho minus y, right? So rho minus y into theta minus rho theta over original LDE is again rho theta. So you will cancel out the theta, so we're left with only epsilon x equals to minus y over rho. Again, y, what is y? Y is the distance. Y is the distance in the positive y direction along this above this neutral axis, right? So this is a linear relationship, because there is no quadratic term, there is no square term. So this is a linear relationship. As the y increases, epsilon x increases on the positive side or on the negative side, and when it is 0 at the neutral axis, so epsilon x will be 0, resultingly sigma x will be 0, right? It is minus y over rho, right? So means okay, when we go into the positive direction, positive y towards the towards this surface, compression is there, y is positive, epsilon x will be always negative 1. Epsilon x will always be negative 1, and this also confirms because this is in the compression. And when you go below of the neutral axis, y will be minus. So minus y multiplied by minus y, it will be minus multiplied by the minus, it will be positive 1. So below the neutral axis, it will be the positive epsilon x, and we know positive epsilon x represents the tensile one, right? So this science definitely complies with the situation. Or top surface is in the compression and the bottom surface in the tensile, right? And since this is the linear one, so if I draw this, if you look, so okay, fine, we'll discuss in somewhere in the, so maximum compressive strain occurs on the upper surface and the maximum tensile stress occurs in the lower surface. So epsilon x in this particular case, epsilon x in this particular case will be a negative quantity, and in this case it will be a positive quantity, because in this particular case y will be positive, and in this particular case y will be a negative one, right? Okay, so epsilon maximum will be at the c. Now this is the y displacement, sorry, the y distance, and the maximum distance is c from the neutral axis. Obviously, where it will be maximum, when y will be maximum, and y maximum is at the c. So epsilon max will be minus c over rho for the top surface, this one, and for this one it will be epsilon max will be c over rho, because in this particular case y will be positive, and in this particular case y will be negative one, right? So the ratio of this epsilon was minus y over rho. So epsilon over epsilon max ratio will be this one, minus y over c, and epsilon will be equals to minus y over c over epsilon max. When y will be maximum, it will be c over c will be 1, so epsilon will become maximum. It depends where y is. I mean, on both sides. On the top surface, it will be minus epsilon maximum. On the bottom surface, it will be the positive epsilon maximum, right? And the sigma x Hooke's law, sigma x will be e into epsilon x minus, that will be equal to minus e into epsilon x is y over rho. So it will be the one that will be going to the final expression of this, right? And epsilon, this is what we have already done. Epsilon is minus y over c epsilon maximum. And likewise, if we go for the sigma max, that will be minus e c over rho, and when you will take the ratio of this versus this, so you will end up this expression. It is a almost similar expression. When you have maximum epsilon at y is equal to c, so you will have again maximum normal strain will be normal stress will be there. So when you have maximum normal strain, so you will have maximum normal stress over there. And normal stress we can define in the compressive and the tensile one. Topmost surface will be in the expression in the compressive one, and the lower surface will be, bottom surface will be in the positive one, right? Because there will be tensile forces, right? Now we go for another expression, like now we know that we have already discussed that sum of all the forces equal to 0, because they are on the top surface it is the compressive one, and on the bottom it is the tensile one. So they are equally and opposite. So sum of all the forces will be equal to 0, but sum of moment will not be equal to 0, right? So dF is equal to sigma dA. This is what we have already done, and sigma dA. Sigma is basically minus y over c sigma max dA, and we will simplify it. It will come like this one. And what is this? This is basically the Q, first moment of area, right? And either since it is equal to 0, either this equal to 0 or this equals to 0. This could not be equals to 0. This could not be equals to 0. This could not be equals to 0. So y dA equals to 0, right? And this defines the centroid. This is what we have already done. So means that centroid at which the Q is 0, which is the definition of centroid. So neutral axis is just the centroid of the, right? So it means that neutral axis is passing through the centroid of the object, or the right. Since this is a linear relationship exists between the both, so if we go upward, so all the forces will be the compressive one in this part, and below y, for the negative y, all the forces are basically the tensile one, right? And there is a linear relationship exists between this, because we have just seen that sorry, that sigma was minus y over c sigma max, right? So this is a linear relationship. sigma will be maximum when y will be equal to c. So you have sigma will be equals to sigma max, or and minus sign defines whether the surface is in the compression or surface in the tensile tension, right? Since moment are not equal to 0 again, right? Moment is about the z-axis, so we are applying the moment about the z-axis, and that is not equals to 0. I am again saying again and again, the forces are equal and opposite, so they nullify each other, but the moments are not equal to 0 about the z-axis. So how we will calculate the moment? Moment will be y into df, right? This is what we have already done in the start as well, and df is equal to sigma dA y, right? And when we simplify it, sigma again is y over c sigma max and dA. And when we simplify it, sigma max over c y square dA. Now what is this? This is basically the second moment of area, or moment of inertia I, right? So if this is m, this is sigma max c into I, right? So it will be sigma max will be m c over I. For any other value other than c, for any value other than c, it will be minus my over I, because sigma we know minus yc over sigma max. So sigma max over c, sigma max is over c is minus sigma over y, right? When you put this expression and mathematically solve this one, so you will end up with this one. So this is for the maximum value, because at that it will be maximum will be at c, or any other value other than c from the neutral axis existing at any point y, so you will use this one, right? So if you remember last time when we calculated the torsion, that was tau max was Tc over J. Now they are similar expression, right? Now we are dealing with a bending, so we are using moment. There we were using rotation, so we were using torque. C is same for both. This one is C, same, right? But the I is here, it is the second moment of area, moment of inertia, and here it is the polar moment of inertia, because we are dealing with the rotation. So these are the similar sort of expression, except in this particular case we are dealing with the bending, and in this particular case we are dealing with the rotation only. So they have the similar type of the expression for both chapter 3 and 4, and both are maximum on the outermost surfaces, right? Both are maximum. Torsion is again maximum at the outermost periphery, and the bending and the sigma in case of bending is also maximum on the top and bottom. Obviously one is in the compression, so one will be the positive one, one will be the negative one. The compression will be the negative one, whereas the lower one will be the tensile one. So that will be the but the maximum stress, irrespective that you are getting compression or tension, both are at the maximum surfaces. So both pure bending case or for the torsional, you will get the maximum torsion or the maximum bending at their outermost peripheries, right? This is another expression that is called sections one, right? This is simple the the recalculations or the modification of the similar the expression. Now sigma max is mc over I and m over s. S is called section modulus, section moment of inertia, or the section modulus, right? Sorry, I is the basically section moment of area, and S I over C is the section modulus of the one, right? So in terms of section modulus, sigma m will be m over s, or s we know I over c का expression हमारे पास exist करता है, right? What is the importance of this one, right? Now you have two objects having the same cross-sectional area. Look, this one, they have the same cross-sectional area, 4 into 6 into 4, 24 inch square, and 8 into 3, 24 inch square. So they have the same area, right? So if we calculate this for this section modulus I over C, this is a rectangle section 1 over 2 BH cube, and section and the C centroid, C is the basically the center distance, right? So that will be h by 2 at the neutral axis, right? So it is the neutral axis h by 2, and 1 over 6 bh square equals to 1 over 6 ah. Since area is constant for both, the section modulus is dependent on the height. The larger the height, larger will be the section modulus, and section modulus has inverse relationship with the sigma max, right? Sigma max is the normal strain. Larger the section modulus, smaller will be the maximum stress, right? So this is the same I just discussed, वो जो मैंने फटे वाली एग्जांपल दी थी, यहां से भी वो चीज साबित हो रही है कि मैंने अगर उसका h बढ़ा दिया है, ठीक है, आई हैव इंक्रीज द h, तो मैंने उसका सेक्शन मॉड्यूलस भी बढ़ा दी। सेक्शन मॉड्यूलस बढ़ने की वजह से बेंडिंग जो है, या सेक्शन मॉड्यूलस बढ़ने की वजह से मैक्सिमम स्ट्रेसेस भी कम हो जाएंगे, बिकॉज सेक्शन मॉड्यूलस हैज इनवर्स रिलेशनशिप विद द मैक्सिमम stresses. So larger the section, keeping the area same, will have lesser stresses as compared to the one which has the lesser section modulus. Or section modulus we have already discussed that it depends upon the height if area is constant there, right? Fine. And last slide is basically the elastic formula for the bending. We have seen that whenever we have this curvature, right? This is the curvature, and rho is basically the radius of the curvature. But what we want to calculate? We want to calculate under certain load. We want to calculate what curvature it will get, right? So larger the small, as we keep on increasing the load on this particular one, rho keep on decreasing. Rho keep on radius of curvature, that is rho, is keep on reducing as the load keep on increasing, right? So what about the curvature now? We want to calculate the curvature, right? Curvature is always calculated by taking the inverse of the radius of curvature, and radius of curvature I know is rho, right? So 1 over rho will be the radius of curvature, right? So this is the expression we have already calculated, that epsilon max was sorry, epsilon max was rho over c, right? This is what we have already seen, right? So and obviously, sorry, c over rho, c over rho epsilon max, right? Okay, fine. This is the equation 4.9. We have already discussed it, right? And epsilon max is, Hooke's law says sigma m over E. This is the Hooke's law, right? Sigma max is E epsilon m, or epsilon m is sigma m over E. When we put this expression into this one, epsilon m, so I'll get sigma m over EC, 1 over EC, and sigma m I have already calculated MC over I. So 1 over rho will be m over EI. This will give me the curvature, right? So whenever we want to calculate the curvature, so we can calculate by having this expression. M obviously is known to us. I we can calculate. E is the material property, that is the Young modulus or of that particular material. So from that we can calculate. So what it tells, under certain load condition, how this curvature will be there, and taking inverse of this, we will can calculate what will be the radius of curvature for that particular body, right? So here I end my this lecture. So theory of banding chapter 4 has been completed. In the next lecture we will start doing the mathematical stuff for all this, and then we will see how our numerical part or the mathematical part of this particular section proceeds. So thank you very much. So in next lecture we will start doing the some mathematics and the numerical shares. Thank you.